Hello, this and my other YouTube videos are extracted from the History of Man series, currently 6 books published in print, ebook, and most importantly, audiobook. I'm a storyteller, and if you like these video stories, you'll love the History of Man series audiobooks. Great for commuting, or just sitting back and relaxing. And unlike a novel you've read where you know the ending, you can listen to these books on tape more than once. There's so much to learn. Available on Amazon and audible.com, I narrate the audiobooks. And the best part about that is you can listen to these stories without having to look at my stupid face. And with that said, let's get the show on the road. Hello, I'm John Bershoff with another installment of History of Man series. Today's subject, why the Krebs Cycle? I need a board to do this because there's equations. I don't understand this unless I have equations. We think of oxygen as fundamental to life, and it's true with animals and even plants. Although plants take in carbon dioxide and release oxygen, they still need oxygen for their version of a Krebs cycle, and plants need oxygen in the dirt for the absorption of nutrients. But the first bacteria on Earth in the soupy oceans derived energy from several processes that did not require oxygen, that evolved in a reduction atmosphere. Those stage 1 bacteria grabbed nearby chemicals. They absorbed them from the oceans and harvested the stored energy, like hydrogen sulfide. The sun produced hydrogen sulfide, a nearby bacteria grabbed it and broke it down. And by breaking it down, electrons from higher energy state to lower energy state pushed out ATP. It's a classic reduction reaction. Reduction atmosphere to you and me means that the stored energy and chemicals that arose de novo from the sun's heat and available elements and molecules were reduced inside the bacteria. Those energy sources were available in the soupy oceans because it's really all about proximity and valence electrons and temperature, the old Bunsen burner thingy in high school chemistry. The sun created energy-rich chemicals because it could. And then bacteria absorb those chemicals because they could. But bacteria soon learned not to rely on nearby energy sources they could soak in. They learned to make their own energy source in steps. The beautiful photosynthesis reaction, carbon dioxide plus water and sunlight, gives you the backbone carbohydrate structure, carbon, hydrogen, oxygen, and it releases oxygen as its waste product. These were called cyanobacteria. And what that meant was they used the available carbon dioxide in water and sunlight to push out the carbs they needed for energy. But even those carbohydrates, those homegrown carbohydrate energy compounds inside these cyanobacteria, these original stage 1 bacteria, the energy harvested was still by reduction, either fermentation or anaerobic respiration. Fermentation is taking glucose to pyruvate, and the end products can be lactic acid or ethanol, or anaerobic respiration, and these are one-way reactions, produces lactic acid. And when these compounds are being broken down, the electrons are then pushing out ATP. But even these processes of harvesting electron transport from these products had its issues. Now, the term electron transport is a fancy schmancy phrase, but all it means is that high energy electrons stored in either absorbed nutrients or the homegrown nutrients from the photosynthesis were transported to low electron energy states. As they dropped down in energy levels, they kicked out ATP. ATP is the energy currency of all cells on Earth and likely arose from the beginning. ATP goes about the cell, giving up its energy state to horsepower literally every reaction inside the cell, from cell division to making enzymes to transporting goodies into and out of the cell. It requires ATP. Now, These reactions are called redox reactions, reduction oxidation reactions, and don't let that phrase scare you either. Surely it did scare me in chemistry. Redox reactions, all it means is that when one chemical is being reduced, when its electrons are dropping down in energy state, another chemical is being oxidized. It's grabbing the energy from those electrons. Its electrons are being elevated. Oxidation reactions don't always require oxygen. It took me a little while to learn that one too. It's just that the first oxidation reaction involved oxygen, and it was the Krebs cycle, the gobbling up of electrons in that horrible to remember Krebs cycle. Now, if you're wondering why gaining electrons is termed reduction, you're gaining something, but it's being reduced. It simply means that its ability to gain more electrons has been reduced. It has too many. Its corollary, if a substance gives up electrons, it might want them back. Its ability to then gain electrons back implies its oxidation potential has increased. That's all redox reactions are. So the first bacteria on Earth, stage one, they either absorbed energy-rich chemicals made by the sun, or they had photosynthesis. But the problem was, in these reactions, there was dead-end reactions, and the chemicals that were at the dead end of these were useless to the bacteria. They were actually poisons, such as lactic acid and ethanol. Although ethanol might make the bacteria drunk happy, it's still a poison. The bacteria then had to get rid of these chemicals. And that's not only a pain in the butt, but it's the expenditure of ATP. So they make ATP and produce these end products that are poisonous and have to use ATP to get rid of them. In an example, a single compound of glucose from fermentation reduction only yields 2 ATP. It's not very efficient. Whereas in the Krebs cycle, we'll get into that again, a single molecule of glucose gives you 32 ATP. That's quite a difference. So as mentioned, early bacteria eventually converted to photosynthesis, cyanobacter, blue-green algae, plankton, using CO2 and spinning off oxygen, which was a waste product. Imagine that. The oxygen we breathe is the waste product of photosynthetic bacteria, and now plants too, which plants evolved from bacteria, as did we. And after 1 billion years or so, when enough oxygen from the cyanobacteria populated the atmosphere, it set the stage for aerobic respiration, the avatar of oxidation reactions, the oxygen O2 molecule, and the creation of the Krebs cycle. So photosynthesis, plants, gave us the carb backbone, but breaking down that backbone with fermentation or anaerobic was not good. So in steps the Krebs cycle. What happens in the Krebs cycle is pyruvate enters at the top, 6 carbons, and it eventually goes through the cycle to a 4-carbon compound, oxaloacetate, and it changes configuration as it's doing that. But as it does this, it's a cycle, and oxygen was needed for this to occur because oxygen gobbles up electrons stored in these carb compounds. So the key feature about the Krebs cycle is that oxygen loves electrons. It allows for the cycle to be a cycle. The efficiency of converting high energy electrons in a 6-carb along the transport, as well as more efficient transport, it's more efficient than the reduction transport, and there are no waste products. So the end product of this cycle is a compound that can then go back into the Krebs. That was not the only important for bacteria. It was not only important for bacteria to develop the Krebs cycle. I mean, it made their life a lot better than having poisons to deal with and inefficiency energy. I mean, the cyanobacteria that developed the Krebs cycle were pretty happy. But more importantly, it allowed for evolution on Earth to occur. You can't very well go from a unicellular life to multicellular life if your energy processes are inefficient and if those processes end up with poisonous waste byproducts that had to diffuse out, either actively or just diffuse out. but they were still waste products, and they could kill the cell. Lactic acid, ethanol. So the Krebs cycle evolved a cycle with no waste and more efficient in grabbing electrons for construction of ATP. And the reason it's more efficient, oxygen. Oxygen becomes the patsy to accept electrons. More on that in a moment. The more oxygen pumped into the atmosphere by cyanobacteria, the better chance life on Earth could convert from a reduction atmosphere, reduction energy reactions, where chemicals gave up electrons, to an oxidation atmosphere where especially oxygen accepted electrons. This evolutionary leap, coupled with the indispensable nature of water, allowed for unicellular life forms to evolve into multicellular life forms. It favored evolution. So the key thing to remember about the dreaded high school biology class Krebs cycle that at least my teacher did not emphasize is oxygen. Oxygen loves electrons, even electrons at low energy states. No other chemical gobbles up electrons like oxygen. Oxygen's ability to efficiently accept the lowest of low electron energy states is the key to the Krebs cycle. Each step of the Krebs cycle has some funky equation, which they made us memorize for exams, and then we would forget them. So we forget them, but the important thing is that the sugar breaks down step by step from a 6-carbon to a 4-carbon, or it changes configuration. And with the change in configuration, electron energy is transferred to building ATP. In fact, there are 4 places where ATP is pushed out. There's also NAD, NADP as an intermediate to ATP, but that's another story. Every time the sugar loses a carbon structure from 6 to 4 or changes 3D configuration, ATP is pushed out. No one wants low energy electrons, particularly when you get down to here, except oxygen. Oxygen is the patsy. It will accept, as stated previously, the lowest of low electron energy states simply because it loves electrons. Oxygen drives the Krebs cycle. And once you appreciate that oxygen is at the end of this cycle with its mouth wide open, gobbling up electrons, memorizing all those intermediate steps for an exam is just memorizing. The why makes it easier to understand and memorize the how. One molecule of glucose in the Krebs cycle makes 32 ATP, and the end product, oxaloacetate, with an enzyme, acetyl-CoA, is converted back to citrate, pyruvate, and the cycle begins again. Efficiency, no waste. In comparison, fermentation and anaerobic respiration, the same one molecule of glucose only makes 2 ATP. It's a dead-end process, and it has poisonous waste products. One other point. Each step of the Krebs cycle, as oxygen is swallowing electrons, the chemical step-down product produces carbon dioxide from the carb structure, which is sort of a waste product. It's the reverse of photosynthesis. So inside the cell, these carbs are being broken down from 6 to 4 carbons, and carbon dioxide is being released in the cell, and then it has to diffuse out. With multicellular life that breathes like you and me, as blood absorbs oxygen in the lungs from the inhaled air to bring oxygen to each cell and every cell, simultaneously, the blood absorbs from each and every cell their carbon dioxide and exhales it in the lungs. It's a beautiful symphony made possible, besides oxygen, by water, hemoglobin, red blood cells, blood vessels, and pumping heart, and the stellar job the lungs perform. Oxygen and carbon dioxide wave to each other in the lungs, one coming in, the other going out, like passing ships in the night. I hope you enjoyed this episode of the Krebs Cycle, the History of Man series. I write books. I have 6 out in the History of Man series. It's the first History of Man. It's a style of writing called jumping off. I have a base subject, which is usually medicine and science, and I jump off into other stories, history, geology, philosophy, astronomy, you name it, art, music. I always come back to the baseline story, but it's not a style of writing that's good for everybody. But I promise you, with every turn of the page, metaphorically, you'll probably learn something. I certainly did. Anyway, the books are available in print, Kindle, an audiobook. I hope you enjoyed this Krebs Cycle story. I hope you have a good day. Thank you for listening. Be well. Thank you.